Hi, this is Tom. We're going to talk about time series. So we're dealing with a linear state space model again. And we have the following representation where xt is an n by 1 vector of random variables. A is an n by n matrix. C it is a, let's say, an n rows by p matrix. Wt plus 1 is a p by 1 IID, independently identically distributed random vector, and it's distributed as Wt plus 1 is going to be normal, zero, multivariate normal, zero mean, and identity covariance matrix. And finally, we're going to run this system star for t equals 0, 1, 2 on forever. So that means we need an initial condition, and our initial condition is going to be x0 equals, we're going to make that distributed as normal with some mean vector and some covariance matrix sigma 0. And sigma 0 is going to be a positive definite matrix. That's what I mean by this. Okay. So we can map many examples fall within this setting. Okay, and we've given a number of such examples. Well, let's give one more. Just going to raise an issue. Suppose that we want, well, also just say one more thing. Once we also specify a vector yt, which we say is perhaps an m by 1 vector of observables, we're going to just have that be a linear combination of the state. So our complete system is this. We always have to say what the initial condition is. So we have given a number of examples. Well, here's another example that is useful. Let's say that yt is equal to a constant a plus b times time plus c times time squared. So it's purely deterministic, and we're going to start this off for t greater than or equal to 0. So this is going to be a quadratic polynomial in time. How would that fit? So the way we always do this is we sort of do what we did last time. We're going to need this times a shock. Well, this process, there's going to be no shock. So I'm just going to make a guess. Well, how about this? 1 t and t squared. Well, that, once I say this as a state, this is going to be my state. That's my state. Then the next period, my hands are tied. This is going to be t plus 1 squared. So the only way this is going to work is now I fill in this matrix. 1, 0, 0. Oops, I made a mistake here. This is t, of course. This is t. This is t plus 1. So this is going to be 1, 1, 0. And then if we do a little algebra, t plus 1 squared, that's equal to t squared plus 2t plus 1. So that means in this third row, I'm going to have a 1, a 2, and a 1. So this is my state space system. A is equal to 1, 0, 0, 1, 1, 0, 1, 2, 1. And then I'll just make my G. So if I want yt equals a, if I pick a, b, c times the state, 1t, t squared, everything works. So my G looks like this. It's a 1 by 3 vector. So that's just an example. So many systems, linear systems are going to fit into our framework. Notice this is a linear system, even though it's a linear system in the state, even though the state itself is a quadratic function of time. Okay, one other thing is that's going to come up is this matrix A. I will often assume that the eigenvalues of A are less than or equal to, or sometimes I will say strictly less than. Sometimes I'll say 1. And I will either say in absolute value, I'll either say 1, or sometimes I'll say something like 1 over root beta, where beta is going to be a discount factor. So I don't want the eigenvalues to be too big. Okay, and that's going to be a condition. This is a stability condition, a certain kind of stability condition. And in particular, I will say A is a stable matrix if it satisfies one of these conditions. I know I'm being a little vague, but different conditions we're going to impose in different settings. That's where we're going. Okay. And let me remind you of something. It's going to be a remark. It's going to be very useful. If the eigenvalues of A are distinct, then they can be represented. Then A, the matrix A, can be represented like this: P lambda, P inverse, where lambda is a diagonal matrix. It's a strictly diagonal matrix of eigenvalues. And P is an n by 1 matrix whose columns are the eigenvectors of A. We're going to see this a number of times. And this is a representation of A in terms of its eigenvectors and eigenvalues. And what P does, it's also true that the columns of P well, we'll see. This is kind of a remark, are orthogonal when A is a symmetric matrix. When A is a separate positive definite matrix. We'll use that later. It's a theorem from linear algebra that we're going to find useful. Okay, so if we have A equals P lambda P inverse, okay, then we can compute A squared. Well, that's equal to P lambda P inverse, P lambda P inverse, which is equal to, that's the identity, which is equal to P lambda squared P inverse. And if you iterate this, you'll find that A to the J is equal to P lambda to the J P inverse. This is a very convenient formula because it shows how raising A to a power, what this equation tells you, this is going to imply, so the eigenvalues of A to the J equal the eigenvalues of A raised to the Jth power. This also tells you the eigenvectors of A to the J equal the eigenvectors of A. And those are properties that will remind you from linear algebra, and they're going to be very useful for us. Okay, so to remind you, we have computed some moment formulas. And I'll remind you of those. For a linear state space system, as we have, we said E, the expectation of the vector X, was a vector, it's an n by 1 vector, which we called mu. And then we said that we took this covariance matrix and we call that sigma t. And we derived some formulas for this. And remember, what we're doing when we compute mu, what we're doing is, so E of xt, that's a shorthand. We have xt is really, it's a random variable. It's really the integral. That's what expectation means, and so on. You have to remind yourselves. So we did a little work, and we found that we got a formula for mu t, which is a difference equation, which was very pretty because what it says is the mean vector follows the non-random part of the difference equation. Because remember, the difference equation so basically when we took the mean, this canceled out to 0. And that's how we got this equation. And then we got this other equation, which was a little more. We did a calculation and we found that this was true. So this is this is an equation for the, this is a deterministic difference equation for the covariance matrix. And then we asked a couple questions. We asked the questions of, do these converge as t goes to infinity? Starting from, well, what initial conditions? Starting from our given initial conditions, u0 and sigma 0. We asked that. And do they converge? And if so, to what do they converge? So I'll tell you some answers that we're going to use repeatedly. The answer is yes, if, and I'm not putting only if here, if the eigenvalues of A are bounded in absolute value strictly below unity. And that's true for both of those. So they'll both converge under that condition. Just to remark, they will also converge under some other conditions that have to do with how A and C fit together. So it's possible that this condition is violated, but A and C can fit together in just the right way, so it's still okay. And that has to do with a partition of A having its eigenvalues strictly below unity. We'll talk about that. Actually, if you look at Appendix B of Chapter 2, you'll see what I'm talking about there. So see Appendix B of Chapter 2. Okay, so if they converge, where do they go? Well, mu is going to have to satisfy this equation. And sigma is going to satisfy this equation. And this equation, we'll spend some time talking about this equation. This equation, if all the eigenvalues of A are strictly less than unity, then the only solution of this is mu equals 0. This equation is called the discrete Lyapunov equation. Or Sylvester equation. And acceptable ways to solve this equation are just to iterate on this equation. If you iterate this equation just starting from t equals 0, in other words, we'll iterate on this equation. Starting from sigma 0, and we'll drive t to infinity. That will converge under the conditions. So that's one way, not the best way, but it's one way to solve the discrete Lyapunov equation. Okay, and one more equation that we computed, which is important. We computed this object, E of xt minus mu t, xt minus j minus mu t minus j. We computed the cross covariogram, and we computed that that was equal to a to the j Actually, I want to do this differently. It's going to amount to the same thing, but you'll see why I'm doing this. It's great that I can erase. I spent a lot of time erasing. We calculated that this is equal to a to the j times sigma t. And this depends on both j. J is the gap in time between the two dates at which we measure things. It depends on j, the gap in time, and on the initial date t. Except when sigma t equals sigma is independent of time. Okay, so the situation is when sigma t equals sigma for all t, and mu t equals mu for all t. We say the process is said to be covariance stationary, in which case E of xt plus j minus mu t plus j, well, actually, minus mu, can erase xt minus mu transpose, that's just equal to a to the j times the sigma. There's no t. I don't need to keep track of the t there. Okay. Another important concept. Impulse response functions. Applied economists are talking about these a lot. So let's take our system, xt plus 1 is equal to axt plus c wt plus 1. Their system. Whether or not I impose conditions on the eigenvalues of A, the stability conditions, that's going to matter for some things, and it's not going to matter for others. That's our system. So we're going to iterate this. This is true for t equals 0, 1, 2. If we iterate this equation, it's going to imply this following representation. xt, well, let's just do a couple. I'm going to get x1 is equal to a x0 plus c w1. x2 is equal to a x1 plus c w2 is equal to a, now we'll just substitute in, a x0 plus c w1 plus c w2. If I just keep going, well, this is clearly a squared x0 plus a c w1 plus c w2. And I just keep going. I'm going to get x to the t is equal to a to the t x0 plus this thing, j equals 0 through t minus 1, a to the j, c, wt minus j. And the coefficients, remember they're vectors, the coefficients, this is going to be a sequence, AJC, j equals 0, 1. Typically, we can go off to infinity now. So what is it? That's C, AC, A squared C, A cubed C. Notice how we're raising to the power. Keep going. These are called impulse response coefficients. Okay, so that's what they're called. So you can ask, what question do impulse response questions, the response coefficients answer? Question. Well, they tell you the response of xt to a shock W1 for t equals 1, 2. That's what they're answering. That's the answer. And if you stare at our equation, you'll see that's what we found. And it's going to follow from this that it's going to be easy to deduce the impulse response function for y. That's just going to be this. And that's going to go good. And so on, where y0 is equal to g x to the 0. Okay. Oh, just a remark. If you see that I make mistakes with the equations, it's your job to tell me. I don't put them in intentionally, but sometimes I do. By mistake. Okay. Well, now we have machinery, and we can give a very concise presentation of the theory of prediction. And this is an important topic in the history of probability, statistics, and economics, because expectations about the future are really important. And what we're going to do is get some prediction formulas that because we've adopted this linear state-based system, they're going to become extremely useful. They encompass many of the classic formulas, but you were using minimal mathematical machinery to derive them. They're not the way they were originally derived by Wiener and Kolmogorov, giants of the 20th century applied mathematics. Applied for Wiener. I don't have to say applied for Kolmogorov. Okay, so we have our system. Let's write it down. With our distributional assumptions about WT plus 1s, the IID, and our distribution assumptions about x0, our initial conditions. Okay, the first thing we're going to do is we want a theory about, key thing is x, t, this process, is Markov. And you know what that is from the readings. It's a very important process. I'm going to just say this. Yt is not Markov in general. And that's going to be important a little bit. But xt is Markov. You might be puzzled by this, but think about it. We'll come back to it. Okay. So that what we want to compute is the conditional expectation of xt plus j condition on xt. Xt minus 1 all the way back to the beginning. But because of the Markov property, we have this is true. And then it's easy, and I want you to verify this, to verify that this conditional expectation is simply a to the j xt. That's our first killer formula, or killer app. And then the second formula is we can compute the conditional covariance matrix. What is that? Something Lars Hansen and other finance people are using all the time. I'll be very pedantic and write it out. It's a covariance matrix, so I do this. There we go. I put my prime on. That has a very nice formula. That, you can verify that that is this sum. H equals 0 to t minus 1, AH, C, C prime, AH prime. That's my conditional covariance matrix. So these are two gold star, we'll give them gold star formulas. Now, one thing you might ask, you might stare at these. And stare at this one in particular. You might ask, you might take the limit as j goes to infinity. And then this right-hand side is h equals 0 through infinity, AH, C, C prime, AH prime. And that's the limit of the conditional covariance matrix as the horizon h goes to infinity. As the horizon j goes to, whoops, I made a mistake here. Let me just do this right. Yeah. Yeah, that limit is going to be this. Oops, I just see a mistake. This should be, this upper limit should be j minus 1. Yeah, that makes sense. Okay, so now I have, what's the limit of this as j goes to infinity? Right here. Well, this is going to approach something, sigma. It's going to turn out that's going to be actually equal to this. So the limit of this thing approaches the solution of our discrete Lyapunov equation, which makes sense. The limit of the conditional covariance matrix as the horizon goes to infinity just becomes the limit of the, just becomes the unconditional covariance matrix in the stationary case. Okay, that's kind of a mouthful and it's a side. Okay, so now we have our theory of prediction. Our two gold standard things. Let's use it for something. It's going to turn out that something that occurs repeatedly and I'm going to call this you're going to see, I'm going to call this a Bellman equation, which you've seen before. Going to be, you're going to ask why I call this a Bellman equation. We'll talk about that. So here's what we're going to do. I'm going to use the want operator. I'm going to have yt equals gxt, and I'm going to have my linear state space system. And the problem that occurs over and over again, we'll see why, something you'd like to compute. We want to compute this object. E of summation, j equals 0 through infinity, a geometrically discounted sum of future y's conditioned on xt, and I'm using the Markov process. I want to compute that. Where beta, now what about beta? I'm going to say it's a discount factor that's between 0 and 1. And I'm just going to warn you, some people drive the discount factor above 1 and they still have valid computations. We'll come back to that. So that's what I want to compute. And I'm going to call this thing hxt. I'm guessing that it's a linear function of xt. And I'm exploiting the Markov property of x here. Even though I said y is not Markov, x is Markov. So here's how we're going to compute this. I'm going to show you two ways to do this. Method one, we're just going to calculate and stare. So here's what we do. I'm going to write out the sum. Well, write it out. Let's go. Yt plus beta, yt plus 1, plus beta squared, yt plus 2, plus blah, 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 forever. But this is equal to gxt plus beta gxt plus 1, plus beta squared gxt plus 2. Blah, 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 blah. So now what this is equal to, it's equal to g xt plus beta xt plus 1 plus beta squared xt plus 2 plus blah, 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 blah. And now, and this is the thing I want to compute. I'm calling this thing, what are we calling this thing? Call this thing ZT. But that's not quite what ZT is, because I want to compute, if this were ZT twiddle, ZT is the conditional expectation of ZT twiddle, conditional on XT. Well, so what do? I take this thing and I compute conditional expectations. So that's G XT plus G plus XT plus beta A squared X, plus beta A XT plus beta squared A squared XT So I'm taking conditional expectations term by term, which is equal to G I plus beta A plus beta squared A squared plus whatever times XT. This is starting to look beautiful. So this is equal to G, and I'm going to use geometric series. This is a matrix geometric series. And this term, this is called a resolvent operator. And this thing is a well-defined inverse under the conditions that the eigenvalues of A are strictly less than, well, actually, 1 over beta. But I've assumed they're strictly less than 1, so I'm okay. So this is my solution. HXT is equal to this. So my geometric sum that I want is G is equal to HXT, where H is equal to G I minus beta inverse XT. That's our formula. By beta A. So this is predicting a geometric sum, and we're going to see things like this all over the place. Very important in some a whole number of models.